Hi everyone, my name is Nona and I am PhD student at KTH Royal Institute of Technology in Sweden. My research mainly focuses on applying machine learning methods to physiological signals, mainly brain electroencephalogram, which is widely known as EEG. However, in this presentation, I'm going to present our study about a more fundamental problem, which is the importance of independent test set in training machine learning methods. Specifically, we talk about how small adjustments of deep learning models based on the test data set, especially when we have small data sets, can result in significant overestimation of its performance. This study was a joint effort by me and my co-authors, Antonio Ribeiro, Miguel Wachko, and Danica Krejcik. So, deep learning has completely changed the game in so many fields, and honestly, it's all thanks to three reasons. First, availability of large data sets. Second, powerful GPUs. And third, improved training techniques. These have enabled deeper models to learn more complex representations compared to traditional methods and outperform them in many domains. So deep learning works amazingly well with big data sets. So it's also tempting to apply these deep learning methods to smaller data sets, which are very common in fields like medical diagnostics and neuroscience. However, small data presents unique challenges such as the risk of overfitting and unreliable model evaluation. Small data sets are pretty common in human studies for a bunch of reasons. First, collecting data is expensive. Participant recruitment alone costs a lot, and sometimes part of the data collected ends up unusable due to technical issues or setup limitations. Given these high costs, gathering a ton of data isn't always realistic, especially early on when we're still figuring out if the data is even useful. On top of that, sessions need to be short to avoid participant fatigue and loss of attention, which naturally limits the number of trials per person. So increasing the sample size isn't always an option, meaning that researchers have to make the most of the small data sets they've got. So a typical machine learning pipeline involves multiple steps. First, data collection, algorithm selection, and parameter tuning, feature selection, and finally, model evaluation. The way we perform these steps, especially model evaluation, significantly impacts the reliability of our results. We usually split the data into training, validation, and test sets to tune the hyperparameters and evaluate the final model. The approach we take for this splitting often depends on the dataset size. When we have a large enough dataset, we can split it once and reasonably assume that each subset represents the overall data distribution. In this case, we use training and validation sets to develop the model and fine-tune features, while the held-out test set remains untouched for final unbiased evaluation of model performance. For smaller datasets, we use cross-validation to avoid biasing the model toward a specific data split. Nested cross-validation helps with this by using two loops. First, an inner loop for model selection, and second, an outer loop for performance evaluation. Note that the test set here stays completely unseen during model development and training. However, researchers sometimes skip an independent test set due to limited data or make small tweaks to the model based on its test performance. Our study focuses on this issue, especially examining early stopping as one of these seemingly minor adjustments that can significantly impact performance estimates. Early stopping is a widely used regularization technique where training is stopped once validation performance stops improving. While this prevents overfitting, it can also lead to misleading performance estimates if not carefully handled. In this work, we show that in small datasets, selecting the earliest stopping point based on validation performance alone can lead to an inflated estimate of model performance. This effect is amplified in deep learning models. To systematically study this bias, we conducted 3 sets of experiments. First, with real physiological data, and for that we used EEG signals. As I said, my specialization is in EEG signals. Second, we used synthetic time series data to mimic EEG characteristics, and this was to take control of parameters such as channel size and window size. And third, we use Gaussian random vectors as a control to isolate neural network properties. So let's start with the real EEG data. Here we use EEG data from 52 participants in an olfactory task, each with up to 140 trials. Note that for EEG signals, we need to train the network per participant. It's very hard to transfer between the participants because of their differences. So this means that for each participant here, we have at maximum 140 trials. We assigned random binary labels to pre-stimulus data, which represent the baseline activity of the brain. Then we trained 2 different convolutional neural networks for a binary classification task, where EEG signals were labeled as class 0 or 1 randomly. And we used nested cross-validation for training and performance assessment and compared its results with standard cross-validation. But here is the twist. We assigned random labels to the data. If our models were truly learning something, they should perform at chance level. But when we use regular cross-validation, we saw artificially high performance just because of using the same data for early stopping and evaluation. To control factors like sample size, number of channels, and window size, we created synthetic EEG-like time series signals. As we could generate as much as samples as we wanted, we generated 5,000 test samples and used it as a held-out test set. Then we used cross-validation to train and early stop the model. We observed a significant validation test gap, which decreased as the sample size increased. We also checked if window size or the number of EEG channels had any effect, and it turned out that more channels resulted in slightly bigger validation test gap, and larger window sizes didn't seem to change this gap that much. So it's really about the sample size more than anything else. As you could see in the previous slide, for example, like when we had very small data sets, the bias was very large, significantly large, and we will see this also in our final experiment much more clearly. So let's start with the final experiment. To further isolate neural network properties, we trained multi-layer perceptrons or MLPs on random Gaussian vectors with a few number of large eigenvalues, as it's the case in real-world data. We used the same training approach as the previous experiment, using 5,000 generated test samples as the independent test set, and we used also cross-validation on the training set to train and early stop the networks. Surprisingly, models achieved ROC-AUC values above 90%, like 95, around 95%, on completely random data, purely due to using the same data for early stopping and evaluation. The bias is more significant for deeper networks, as you can see, like for deeper networks, the lines are more towards the top of the figure. And also for smaller data sets, like we can see around 100 sample, less than 100 sample, up to like 200 sample, we have like up more than 10% of overestimation of the performance, and this is like very significant and can change the game. Like if somebody claims that we got this much better performance. Also, here in this slide, we looked at how network depth and width impacted the validation test gap. So depth matters more than width, as you can see in the left side figure. As we increase the number of layers, the gap between this validation and test performance got bigger, meaning deeper networks tend to overestimate their true performance even more. At extreme depths, performance drops. So as you can see, like for when we have more than 200, when we have more than 64 layers, then we can see that the validation performance starts decreasing, and it's likely due to issues like gradient vanishing. On the right side, we can see the width figure. So we can see width has minimal effect. Unlike depth, increasing the number of units per layer didn't really change the validation test gap that much. We also tested the effect of the patience parameter, which controls how many epochs we wait before stopping the optimization and the training. And the longer we wait, the more bias a performance estimate gets. It's like you allow the model to search more for the weights that work better on this validation set, and like naturally you get better results on the validation set. And if you use that validation performance, like if you use the validation set to evaluate your model, you get highly overestimated performance for your model. You can see, like if we trained our models for 512 epochs, like 500 epochs, sorry, and you can see if you wait for the whole training to finish and then choose the best validation loss, like the epoch where you get the best validation loss as your model, then you can get like 30% of validation test gap for very small data sets. So yeah, I mean, as we increase these patient parameters, we get more and more overestimation of the performance. So yeah, finally, to summarize, excluding an independent test set can dramatically overestimate performance. So selecting the earliest stopping point based on validation data alone can lead to unrealistically high ROC-AUC values, for example, 95% on random data. And this bias is more pronounced in smaller data sets, which we said are more common in human studies, and deeper networks. So we should make sure to use proper evaluation strategies like nested cross-validation, or for example using a held out test set. Usually it's not very feasible for small data set, but nested cross-validation is, to make sure that we get reliable results. And yeah, that was it. Thank you for listening to my presentation. And for more details, you can check out our paper in this QR code. And please feel free to reach out via email or LinkedIn. Thank you.